Okay, so moving on, right? So a quick look at the preceding steps. That's what I was mentioning earlier. Is that so we have firstly core race, right? That's the input layer, and so core race is taking um, from the weather model from different regional models, including ERA 5, Global Wind Atlas, and then we also have very many the VRE technology assumptions like what would be the hub height, and what would be the total diameter, what is the specific power for wind turbines, same azimuth angle and tilt angle for the solar, and then Core's provides the profile, normalized profile for the renewable generation. And then we have other input data like demand for electricity, heat, hydrogen, EV. Then we also have region-wise wind, solar, onshore wind, offshore wind potential, right? Like, of course, when you are modeling it for whole continental Europe, you cannot go at the plant level, but rather you develop to each region level, be it a market region or some for offshore, we have this nuts maps. So we have different region level. So in each region, we know how much is installed wind, solar, other technology. Then we know the existing and planned generating plants as well as the transmission lines in each region. Also, we know the new technologies and their potential. Of course, we have another thing is the fuel cost and CO2 tax. We have assumptions that in toward later part of this decade, we'll have much more CO2 tax, because if you don't put CO2 tax, what is the point of why would you decommission already running technologies? They have become cheaper, right? More and more you run a thermal generator, it starts becoming cheaper because you have already recovered all the initial investment. So a 20-year-old, 30-year-old thermal power plant, you would only decommission if there is a huge fuel tax or if you have CO2 tax. So we also have those regulatory and political inputs. And then we have the economic inputs as well, economic parameters and like efficiency, full load hours, technical parameters, all those things for each technology. And then we run this in a tool called, which is open source tool, by the way, called PAL model, which does both the capacity expansion planning as well as day ahead optimization. And it gets all the input data and to get some scenario kind of data, like where you some of the are user specific inputs. For example, what are your policy targets? What are the technology costs you assume? And how much level of sector coupling you are assuming, because those are quite empirical, right? What do you think in 2030? How much electrical vehicle will be installed? So you can play with those numbers, right? You can put. So these are the sensitivities of the scenario. 50% electrical vehicle penetration. Some conservative people might think 20%. Some optimistic would look at 80%. So all are these kind of positions in your scenario. And then comes all the constraints, like how much the transmission line can go, the EVs or the conventional generations, what are their maximum and minimum technical constraints, hydrogen production constraints, like hydrogen, if you are producing, how much can you store and whatnot. So all those kind of. And when you have run this capacity expansion and the day ahead market model, then you get the results. There are many results in terms of them, but most important one is the day ahead optimization, which we're looking at is minimizing the operational cost of the system to meet the hourly demand for electricity, heat, and hydrogen for all the scenarios, right? And then it gives me the outputs of hourly dispatch of generators, information on the VRE curtailments, that how much VRE is planned to be curtailed in the day ahead market, because you could not accommodate all the wind and all the solar because there is not enough load and you have much more renewables. What does that mean? That you have also room for reserve coming from wind and solar there. And then there is also inter-area power flow between the countries. Why is that important? That means that if there's an imbalance, then I look at my interconnections between Sweden and Norway and Germany, and I know how much support I also can get from my neighboring region. Because otherwise, everybody would have to over dimension the reserve requirements in their own region. And I know that's problem with French Union. You get support being an island system, but for continental Europe, we also the whole concept is that bigger the system and more harmonization with requirement for individual is much less because we can support each other, right? And then also we know that how much storage is being dispatched, so that how much flexibility we have there, and charging and discharging profiles of aggregated electric vehicles, and most importantly, the price profile of electricity, heat, and hydrogen prices. Some key terms which you might need to know. Is that a question or a?
No, it's just a chunk.
Okay. Balancing market. So entirety of institutional, commercial, operational agreements that establish market-based management of balancing. That's the balancing market. Balance service provider, any market participant who can provide the reserve providing units or reserve providing groups. It can be a single unit or a multiple units going together. They are called a balance service provider. Balance responsible party is a party. It can be a market participant or a representative who is responsible for its own imbalance or company. It can be a single generator, or it can be a combination of generators who are responsible for their own imbalances and may handle the balance for the production or for that matter also consumption, and they treat the actual electricity. Then I already talked about frequency containment reserves. I have already talked about automatic frequency restoration reserve. I have also talked about manual frequency restoration reserves. What kind of balancing principles to be employed for future? I also discussed a little bit about it already. So traditional relied heavily on the automatic reserves and the inertia system, moving towards more on the dynamic services, and also mix between automatic and manual reserves, and demand is playing a major role. Balancing markets, again, it was more into the day ahead or bilateral, and I'm talking here more globally, but more and more dynamic reserve markets are coming in cross-border markets, and even if they are market even today, but in even continental Europe, we have dedicated generators providing it, but more and more other kind of technologies like demand side EVs and whatnot, hydrogen, they would play a role in coming years. Reserve capacities or sources who are providing reserves. Typically, it was the centralized power plants, and more we are seeing into distributed energy resources and energy storage and virtual and hybrid power plant. By the way, I should give credit to our postdoc Sumant for making all the slides. I'm just presenting on his behalf. Yeah. I have, or he has made a list of all the countries and what kind of practices is ongoing there. But I will share the slides with you later.
Yeah, sure.
And you can go through them, and it's not comprehensive, but at least you can compare between them with the references and find out how different they are. But what volume of operating reserve will future power system require? So we have example of DK1. Denmark has two parts, DK1 and DK2. And DK1 is connected to the continental Europe and DK2 is connected to Nordic. And typically we have around 3 gigawatt peak load, something like 2.5, 3 gigawatt peak load in each of these regions. And what we see in 2025, so that's next year in our projection, that the standard deviation of imbalance is less than 10% of the wind installed capacity for the respective years in 2025. But when we move to 2045, so if you look at the megawatt in 2025, for example, so 90% of the time, your imbalance is looking at 1,000 to 1,500 megawatt oddish, right? So that kind of balancing reserves you need, be it in Denmark, DK1, or in the neighboring region, to mitigate the imbalance. But when we look at the 2045, for example, the volume is more than 5 gigawatt, right? Because of all the offshore wind plants we are planning here. So you can imagine that 3 times more reserve requirement is coming on. And it's not easy to accommodate 5 gigawatt of reserves, even with our neighbors, with the planned tie lines, to always have them available. So we have to come up with smarter methodologies. So 2 times, 3 times more reserve requirements in all around in Europe and all around the world with the green transition. This is a major point, right? And I will keep on connecting to our hybrid power plant. So it would critically mean that hybrid power plant would probably make much more profit in mitigating imbalances in 2045 than in 2025. And now we need to quantify that, right? And this is exactly what you are going to do in the assignment as well, how to do it for balancing market.
Your question on the...
Yes, I can see
what's
the question.
unit for frequency?
So here the frequency is the frequency in the histogram. So it's unitless. So it's number of occurrences in. So I think it's a yearly data, and with maybe with 5-minute interval. So the total number of things will be 8765 times 12, right? So that many occurrences and this frequency. So the frequency does not really mean much. We could have also made a probability density function where the total PDF, that the area under the curve would be 1. So that is like normalizing with respect with the total number of occurrences. But more important is what's the 95 percentile there. Those are the dashed lines. So how much can the available generation fleet support the balancing requirements? So we took an week example for a week here in Poland, for example, right? It's randomly taken because when you're working with whole Europe, to find out an interesting week in the country is not that easy. So, right, we found out this example. To the black line you can see in the top figure here is the installed capacity, right? And the red line is the online installed capacity. That it means there are some hours when you have utilized the installed capacity. The total installed capacity is 12.7 gigawatt. And so the online installed capacity is much less, and it could be because of scheduled maintenance, because that some of the generators could not find enough profit in certain hours, and they had to shut down in the unit commitment. So the online install capacity is much less in certain hours than the installed capacity. But out of this online installed capacity, it might how much of them are available capacity to provide reserve. So already you are utilizing already many of the generators are operating at their peak, and you don't have the available capacity as the reserve. That is the yellow line there. However, out of even that available capacity, many of them are nuclear. For example, it's Poland, so it will be many of them are thermal, which does not have that much flexibility to ramp up within an hour. Even if they're operating at 80% and they need to ramp up, they have only limited capacity to how much they can do based on their technical capabilities. So the dashed line is the ramp up capacity, what is available at any point of the time. And then the blue one is the ramp down capacity, how much you can reduce the generation in the other direction. Right? So what you can see, so very often we'll see this report, we would need this much terawatt of energy, right? And that terawatt hour of energy is the adequacy studies, which only give the black line. It does not tell anything on any other lines. And you can see between the black line and the yellow line, there's a huge gap. And it might come that there are many hours. And I have been telling this since 2013, since when I started working on this, right? To everyone, to the TSOs, to the academicians, they don't believe, right, that this is going to happen, because this is the whole lobby or the norm of discussion that terawatt hours is important. Of course, it's important. You need the energy requirement. You have them. You build up to meet the terawatt hours. And then, unfortunately, the war happened. And then suddenly people have started to see that this yellow line is almost non-available, because you had installed all the gas turbines, but there were no gas. They were shut down, and then you don't have available capacity. So that black line suddenly started disappearing, and now the balancing is getting much more relevant. That because people were paying 5,000 euro for some hours for the balancing cost for each megawatt hour, which they would in normal they give 10 euros, right? You need that. And then suddenly people started realizing how serious is this problem. And this is gonna be more pronounced in 2045, 2035, 2045, 2055. And then people will start and come blaming because the renewables and start lobbying, because they have not been planning accordingly all the timelines. They have not been planning all kind of reserves. And this would be coming anyways. These are all my grievances and my ranting, being that apart. So what we now put in is that the imbalance happening in this. So this is the available reserve, right? In the bottom here, you can see what are the imbalances happening in that region. And then you can see certain time when the imbalance is much more than the, and this is only 2025, right? More than the available ramp up capacity. What does that mean? During that time, that period, either you get it from your neighbors or you have to live with your automatic reserve, right? If your automatic reserves are utilized during that time, and if a fault happens, then you are moving to a even worse situation of a blackout. This situation will be much more amplified in the future. And so this is just an example with the time series, but we move towards the more statistical model later. And now suddenly not suddenly, but now European agencies like the regulators and the transmission system operators are taking cognizance of this. And then they said, we cannot handle our own imbalances alone. Then we need to have a market, a platform where we can all combine together, come together and help each other. And it cannot be that each of us have their own principles of balancing. Then we need to have harmonization. And then came this platform called MARI, which is for manual frequency restoration reserves. And then there is a platform called Picasso, which is for automatic frequency restoration reserve. Then there is a platform called Terry for replacement reserve. And then ultimately the imbalance happening in order to calculate the netting of whole imbalance is called IGC. And because of the time, I would not go into the details, but they are all in publicly available. And I'll keep some of the slides. I'll share the slides with you. I have slides on Mari and Picasso, and it removed the slides on Terry and IGCC. But I can even bring back the slides. I just hidden it. But now I have explained what is the balancing principle, right? Next question is, how do you implement this balancing principle? And then comes all the mathematics, right? So, what you get is day ahead VRE power forecast, which you use to also give to Balmorel for modeling the day ahead market modeling, like we mentioned, and then Corelate provide you also the overhead overhead forecast. So when you know the day ahead power forecast, not only forecast but the day ahead plan, and because we have already seen that the forecast and the day ahead plan can be quite different. So you can calculate based on the day ahead plan and the overhead forecast what is going to be the imbalance, both in the positive and the negative. So these are positive imbalances. When you have positive imbalances, you use up regulation. If you have negative imbalances, you have down regulation. And based on this, then you develop a balancing optimization model, which is basically a mixed integer linear programming model, which you try to minimize the balancing cost based on the available ramp up capacity or the ramp up generators like we showed before. And so subject to ramp constraints, subject to transfer capacity of inter-area tie lines, and of course you need to meet the power balance constraint. And you do it at the 5-minute resolution for a running window or 1 hour or 45 minutes. And this is a running window and a moving window. So you have to, it's kind of dynamic programming that you activate certain reserves for next 5 minutes or not next 5 minutes, 1 hour later, but then you move 5 minutes later and then you know what you have activated. So you have to take cognizance of that and recalculate your imbalance, recalculate your available reserve, and then activate again for the next 5 minutes. And this way you get the 5-minute resolution balancing reserve schedule. That goes into the balancing market modeling, and then comes the real-time prognosis of the imbalance, which you compare with balancing reserve activation plan and the day ahead plan, like combined together, and then you know what is the real-time imbalance happening. With that real-time imbalance happening has to be handled by both FCR and FRR. So if the imbalance is happening very fast, like a storm coming or something like that, then it will activate the FCR. But if it is slow, then it will activate the FRR. So then we can quantify how much automatic frequency reserve we need. Yeah, so the maths is there for you to look at.
Yeah.
So now we'll give two examples. One is balancing requirements for future European power systems and the operation of hybrid power plants in Europe in 2030. So those two are two separate examples, and that would show that why this, like both the modeling of the balancing food chain, as we call it, is used for system level studies as well as for power plant design and operation. I made it operation here, but or operational planning rather, but Megha will take over the design and sizing of hybrid power plant over. So before we move into these examples, can we? I can take a couple of questions. Maybe it's too much information, but
Information.
but it's a good idea to get a bit overview, and then we can always discuss later at another point. Go into the details. Okay. So balancing requirements for future European system, right? So we have scenarios for 25, 20, 30, 25, 35, and 45. And it's based on, so we have to choose, again, it's quite time consuming, computation consuming. So we chose only weather year. So that means all the scenario years in 25, we know how much installed capacity of each technology and the timeline and whatnot and cost of technology. But the weather, we have assumed that it is same as in 2012. We could have chosen any other year for that matter. The reason for choosing 2012 is that the demand time series, the demand pattern is also from 2012. We don't have demand pattern, how it is evolving over the years. So that's a kind of a strong assumption, but we would probably get to work with that in a point of time. The picture you can see is that each country is divided into many regions. Some of them have only one region, some of them have multiple regions, and each area is called balancing area, and then they are each a bidding zone. So each, you can think of a balance. We are trying to balance each of those area here. So if we look at the day ahead market results, and again for Poland for another week here. So day ahead schedules are in hourly resolution, and only the flexible generators can participate in the balancing market, and hourly schedules are interpolated into 5-minute temporal resolution. And net transfer capacity is transmission capacity minus day ahead power flow. So you can see here the fuel-wise generation time series for Poland as well as for one of the regions. In Norway, what you can see that in Poland in this week, the base load is coal. And I think it's for 20, does it say which scenario is this? By looking at renewable, we can guess. Yeah, it's very low wind and solar. So probably it's 25 scenario. But Norway is highly driven by hydro. This hour is mainly hydro reservoirs. Some of them are run of rivers. And then but it also we can see that both the countries are exporting countries, but the export of Norway is much more hydro driven, so that's much more dispatchable, and export of Poland is much more dependent on renewables, and if there is high forecast error, instead of exporting, it will become importing for those hours. And how do I see that? The black line is the demand, and the top up is done by the renewables, right? The greenish curve is the wind, and the yellowish curve is the solar. Then if we look at the flexible generations with the ramp capacity in Norway here, so coal, natural gas, thermal, hydro reservoirs, flexible renewables are considered flexible here, whereas run of the river, nuclear. And in this study, we did not assume wind and solar to be flexible because we wanted them to be utilized maximum to their capacity. But they can, in future scenarios, we also consider wind and solar to be flexible, but they are not utilized to the maximum capacity. So here you can see the statistics of wind power forecast error for the whole year in 2025, 2035, and 2045 here. So you can look, the scales are changing here. So in standard deviation is 740 megawatt in 2025, 3.7 gigawatt in 2035, and 4.9 gigawatt in 2045. So that huge change is happening. We also saw that for DK1 before. How do we calculate the imbalance? So one thing is that there are two impacts of two causes of imbalance. Even this is a small portion, but there is a hour shift imbalance happening. The reason being, this is how the market operates. So you go in the day ahead market and you bid or you commit this much amount of gigawatt hour for the whole hour, right? Let's assume you commute 100 megawatt hour from your generator. So that means one would assume, or the market or the operators would assume, that you are generating 100 megawatt throughout the hour, and the next hour you said that I would generate 300 megawatt, but you cannot jump from 100 to 300 just like that. There is a ramp up, and during that ramp up, there would be a mismatch. But you have committed energy, you have not committed power, so you would end up generating a bit more in the beginning, and you would rather come down. You can do it in many different ways. You can generate less in the beginning, more in the later, but you have to employ one of them or the other for modeling. But what is for sure that every beginning of every hour, you would see certain kind of spike in the imbalance, and this can be only attributed to the hour shift. And then we already discussed the forecast error, right? So these are the two sources of imbalances happening, which can be prognosed, whereas there are other kind of imbalances coming from contingencies, which is out of scope because they are completely random, completely stochastic. You cannot, you just superimpose that after you have done these studies that I need this much for the contingencies. So when we look at the activated balancing reserves or upregulation in terms of in continental Europe, again I forgot to the year. For TPT is 25 terawatt hour. It's probably 25. But what we see mainly that in continental Europe for upregulation, the biggest player is pump hydro, and then followed by natural gas and hydrogen. Whereas and that can easily also come from Norway, from Nordic. Whereas in Nordic, the major source is hydrogen turbine. This also means that this is the reason everybody wants to put a line to Norway, connect to their country, so that they get a direct connection, get all the hydropower from Norway. But what we also see that in both in continental Europe and Nordic, flexible renewables also coming up as the small top. When we look at the balancing prices, we see that day ahead prices was going up to around the standard deviation was 16 and then the mean was 42. Oh, but then there were some hours when it was even going to 140 euro per megawatt hour. But then up regulation prices there are hours when it is going beyond 200. And so there are extreme levels of price fluctuations happening. And these are determined mainly by backup generators and penalties for VRE curtailments. I should mention that there might be some error in these calculations, and we are trying to fix this. We are still not 100% confident with these results. Even with down regulation prices, we see that it goes up to 500 euros per megawatt hour. Okay, so this was a small example. We have much more results, but for the sake of time, now we also use for system level studies, but we looked at what is the value of wind solar battery hybrid power plant in Europe. And this work was done by our researcher Juan Pablo, and we have a paper. I put the citation also there. It's not shown in there, but it's in the slides. What we see there is that it's the NPV over capex chart, and higher the NPV over capex, better is the profitability, or NPV over capex is a profitability index. So darker blue dots are more profitable. So we see quite some business in the southern Europe, but also in UK, but quite some good business coming up in the northern Europe as well. As expected, not so good business in Sweden and Norway. They are driven quite a lot by hydro, but also some small dots are appearing there, and these are because of the local congestions and the dependency on the run of the river hydro in those regions. When we look at the mix of wind plus solar or battery, all the pink dots are showing where the batteries are coming up, whereas the green dots are showing wind plus solar hybrid. Whereas the green dots are basically hybrids, but it's majorly dominated by one of the technologies, whereas the blue dots are real hybrids, right? Am I reading it correct? No. It's complicated. I think the blue dot is showing when wind is more than 3 times solar. So that means it's solely wind. Whereas, the green dots are more balanced hybrid with wind and solar. It's with an and condition. So, and then the red dots are it's only solar, right? So blue is only wind, red is only solar, green are hybrid. Pink blocks are hybrid with battery. So what we see that quite some green dots appearing all over the Europe. If we want to make, and the technology is cheaper for wind and solar, there is good business all around the Europe, even with batteries becoming expensive. But there are pockets of batteries and those are mainly due to the local grid congestions. So the other way to see that they can be alleviated if you can make more transmission infrastructure planning or more investment in transmission infrastructure. That can be quite costly to do that. And the other option is to have wind solar battery. But more studies need to be done. Then I also have a slide on energy management system, but I think we can skip that. But until now, what we showed here, the day ahead and hour ahead modeling. And I'm taking away all the time from Mega. So, but I did promise to our participants in the previous workshop also talk about dynamic model. So I'll go briefly about that. There's supposed to be a video here which is not running. Maybe because I forgot to put the video file. It doesn't matter. It's 2006 blackout.
Something is coming up here, but
if you play, it would not be right because I forgot to put it works.
Yeah, it is working here.
Okay.
But not in the presenter mode.
So let's try in the confident.
Yes.
Yeah. Okay. So this happened in 2006 blackout. So what happened here is that there's a nice story. It takes time, but I cannot avoid that. So in Germany, a barge or ship was supposed to cross a bridge, and the bridge is supposed to open. And when they open the bridge, they have to switch off some power line for security reasons. And then the ship arrived 1 hour earlier, and they asked for permission to open the bridge. And then they called up the transmission system operator. The transmission system operator did all kind of studies. Everything looked fine. And then they opened the bridge. As a result, the first transmission line started tripping it got disconnected. It got overloaded because of the power started flowing in other routes, and it got overloaded. It got disconnected. That overloaded another line that got disconnected. As a result, there were cascading effect happening, and within few minutes, within 10 minutes, it happened instantly, but I think within 2-3 minutes, whole continental Europe was divided into 3 different regions, each region holding on its own. But in the green region, there was a huge over frequency happening. The frequency was going beyond 51 hertz instantly. In the orange region, there was a huge under frequency happening. The frequency went to 49 hertz. And then the blue region did not have that much impact, and the frequency was quite maintained there. The green region, it was a windy day, but this is 2006. We did not have that much share of renewables. Renewable share was 7-8% at that time. And because of this over frequency, quite a lot of wind turbines started disconnecting, smaller wind turbines, some solar panels, and that helped in bringing the frequency back. But in today's scenarios, the new protection rules does not allow them to be disconnected. They will stay connected, and with 50%, 60% capacity share in Denmark, in Germany, in Belgium, we might see that it will create also a huge blackout in this region, because when the overfrequency goes beyond a certain value, all the generators start disconnecting, and it will be quite time taking, few hours to a day to bring back up whole system. In the orange region, quite a lot of load shedding happened. Portugal, they were doing extensively load shedding because they had also quite some small generators, small wind turbines in the region, and then they did not know how much wind turbines were getting disconnected, so they did much more load shedding happening and load shedding than what probably would have required. Whereas some other region, Spain, also did load shedding, but not as much as Portugal, but quite a substantial amount of load was being shed. So for many hours, people in Europe in this region did not have any kind of electricity. And this is not only inconvenience, this has a huge cost. People are stuck in, like when London blackout happened in 2020, recently, people were stuck in the train for hours in London in the tube. Hospitals did not have power, so it's not only inconvenience, it has huge societal cost. I'm not going to talk about frequency containment and frequency restoration process, but I'll talk about the modeling here. So what do we model? That we get the hour rate prognosis, we get the real-time available power, and we get the online prognosis. Based on that we can calculate the imbalances, and then we calculate the activation of the both the replacement reserve during real time as well as the frequency restoration or the automatic frequency restoration reserve, which we call the frequency restoration process. And the frequency control process is the automatic frequency control process. So here in Nordic, we have the FCRN, which is the frequency containment reserve for normal events like the forecast imbalances. Then we have the frequency containment reserve for the disturbance FCRT, and then the already activated the AFRR and the imbalance. So when you add them, when you add them together, so you get the total aggregated imbalance. Then we have the aggregated power system, which is characterized through its inertia, which if you remember, also changes all the time, depending on what kind of technology are online in the system at that point. And based on that, you know what is the frequency, and that would tell you how much of this FCR and AFRR would be activated when you loop it back. Similarly, we have it for the continental Europe. So here, for an example, we have the imbalance of the Denmark coming in, imbalance of the Belgium coming in, imbalance of Netherlands coming in, imbalance of Poland coming in, and we have the LFC for each of those imbalances. Then you add up to calculate the AFRR. And yeah, we only have automatic frequency restoration results, aggregated AFRR, and then the total imbalance in the continental Europe, which is the total imbalance you saw how we calculate from the prognosis here. And then we have again the power system model, which we also call equation of motion, which is modeled through the inertia as the damping. And then it will tell what is the frequency quality and how much is to be active. In order to quantify the AFR, we have some empirical formulation, and there are other methods as well. I'm not going to go into the details of that modeling, but it's a dynamic modeling with a PI controller here. But if we look at the imbalances after we have activated balancing reserve, means this much amount of imbalance needed to be handled by the real-time reserves or automatic reserves. So we see in Denmark West or DK1, we have imbalances of around 1,000 megawatt coming up, and standard deviation or very small amount of time, but still. Whereas for DK2 in Nordic system, the Denmark East, we see around 500 megawatt in 2025. In the whole Nordic and continental Europe, in Nordic, we see the imbalance standard deviation is around 1,000 megawatt. And whereas, no, it's after balancing. Yeah, exactly. Whereas for, also in continental Europe, imbalance is around 5,000 megawatt. How much AFRR should be available in 2025? In Germany, we see around 2 gigawatt, and Holland, we see 1.2 gigawatt. These are dimensioned to handle 99% of the forecasted imbalance. If we look at the inertia, like we are seeing in Nordic, we have certain hours when it is going as low as 2.4. Second, in 2045, in 2025, today it's around 3.2 to 3.8. So there is quite degradation of inertia. But in continental Europe also there is degradation of inertia, but it's not that much because continental Europe is much bigger system. So if we put some discussions, balancing is becoming more and more challenging. The balancing principles varies in different countries, depends on practices, depends on energy, depends on capabilities and structure of power system. Harmonization is required in balancing, and it is also required for different kind of studies, be it system level studies or plant level studies. And this is where I hand